showing your video. I think it's a lot nicer for the speaker to be giving a talk to smiling faces rather than little black squares. So excellent. So our first talk will be by Ruth Levy, and she'll be telling us about testing isomorphism in the congest model. Take it away.
Hi, thanks. Can you see my slides? Okay. Okay, so I'm going to talk about testing isomorphism in the congest model. This is a joint work with Mote Medina. Okay. So I will start with the standard definition of property testing. A tester with a two-sided error for a property P and proximity parameter epsilon is a randomized algorithm such that if a graph, let's say the object that we test is a graph, so if the graph has the property P, then the algorithm outputs accept with probability at least 2/3. And if G is epsilon far, with respect to some predetermined distance measure from the property, then the algorithm outputs reject with probability at least 2/3. The tester has one-sided error if for graph that have the property, the algorithm accepts with probability which is 1. Namely, the algorithm provides a witness for rejection. Okay, so in this talk, I'm going to talk about a tester which works in the congest model. So the congest model is a distributed model. So I will start with explaining what are distributed algorithms shortly. So the graph G is the structure of the computer network. And there is one computer for each node of G and one communication link for each edge of G. Initially, each node knows only about its immediate neighborhood, and nodes can exchange one message per round. And the main complexity measure is the round complexity. In the congest model, what we have is that each message in each round has to be, the size of each message is bounded by order of log n bits, where n is the number of vertices in the network. Okay, so Sensor et al. Defined distributed property testing as follows. If G has the property P, then every node in the network has to output accept. And if G is epsilon far from the property P, then with probability at least 1 minus 1 over some polynomial of n, at least one node has to output reject. Okay, so there are already many works in this regime of distributed property testing, and this is only a partial list of some of the results from recent years. In this work, we are going to talk about testing isomorphism in the congest model. So what is graph isomorphism? Given a pair of graphs, what we want to know is whether we can find a bijection between the nodes in one graph to the nodes in the other graph, such that the graph that we obtain is the same. Let's say in this example, we have, for example, this node here, which has the label A, and according to the mapping, it is mapped to the vertex here with label 1. And if we follow this mapping, what we get is the same graph. Okay, so what is epsilon far from being isomorphic? So G and H are epsilon far from being isomorphic if more than epsilon times n squared edges need to be removed or added in order to make G and H isomorphic. So this definition is meaningful only for dense graphs. Mostly we will use this definition, but we also have results for sparse graphs. Okay, so now how did we formulate the problem of testing graph isomorphism in the distributed model? Okay, so we have the graph G, which is the network of the distributed is the distributed network over n nodes. And there is some node R which can be chosen arbitrarily. And this node receives a graph H. The graph H is known only to this node R, and R also receives a proximity parameter epsilon. If G and H are isomorphic, where G is the network and H is the known graph, then with probability at least 2/3, all the nodes output accept. And if G and H are epsilon far from being isomorphic, then with probability at least 2/3, at least one node outputs reject. Okay, so here you see there is a large graph. Only one node knows the graph H. And we also considered the setting in which all the nodes know the graph H. This is very powerful, and I will explain later what we obtain if we have this property. Okay, so what are our results? Let's begin with the decision variant, not the property testing. Namely, we want to decide whether the two graphs are isomorphic or not. So we show that we provide an upper bound, which is a randomized one-sided error algorithm that runs in order of n rounds and succeeds with high probability. And we show a lower bound for the deterministic algorithms. We show that deterministic algorithms cannot do much better than simply collecting the entire topology of the graph at a single node and then running some an arbitrary centralized algorithm. So I remind you that the main measure complexity is the round complexity. Okay. So we can see that we have a separation between the randomized and deterministic algorithm for this problem. Basically, both results are reduction to and from set equality. And now for the result in the property testing formulation. So we provide an upper bound that runs for order of D, where D is the diameter of the network, plus log of n over epsilon squared rounds and succeeds with high probability. This is for the setting in which only one node receives the graph H. If all the nodes receive the graph H, then not only that we can test, we can also recover the isomorphism in the case that indeed the two graphs are isomorphic. And we cannot recover it exactly, but we in some sense give a recover with a few errors. Okay, we show that for sparse families of graphs, we also provide a O tilde of the diameter rounds algorithms. This is essentially tight. And overall, all these results are essentially tight up to this factor of log n over epsilon squared, because we show that omega of the diameter rounds are necessary even for constant epsilon, even for constant error probability, and applies also in the local model in which the message size is unbounded. And if in all the nodes receive H as an input, and it also applies to the dense and sparse graphs. So the bottom line is that you cannot do better than this. Okay, so for the property testing variant, so what are the main open questions? Let me see how much time. Okay, so the main open question is what is the complexity of the exact problem for randomized algorithm? So as I said, we have only a lower bound for deterministic algorithms, but it's not clear whether we have what is the right complexity for randomized algorithm. The second question is whether we can have one-sided error algorithms for the property testing variant. The other open question is while we provided upper bounds for dense graphs and sparse families of graphs, there is still a large, I mean, for general graphs, we didn't provide any algorithm. And finally, we think it's also interesting to consider other models in which, for example, the known graph is not known and we can only access this graph via queries, and perhaps other models can make sense as well. Thank you very much for listening.
Thanks, Lois, for the talk. I think we have time for one very quick question if someone has one. So unmute yourself to ask if you.
I mean, I guess I have kind of question about the model. Like, what is the motivation behind the one graph being known to only one node?
Sorry, I did not hear. Let me just make the volume to the maximum. Okay, what was the question?
So what is the motivation behind H being known only to one node?
Okay, so the motivation is that it's simply, I mean, it can work also if you give the entire network the graph H, but you don't need this power. So we just we restricted the algorithm as much as possible. So you need this power only if you want to recover the isomorphism. But if you just want to test, then you actually don't need the entire graph to know this H. So the motivation is just because it doesn't matter, because in either case you have this omega of the diameter lower bound.
Okay, thank you again, Lois. And Asaf, please set up for the talk. So the next talk will be by Asaf Rozan, and he'll be talking about almost optimal distribution-free sample-based testing of K-modality.
Hi, everyone. My name is Asaf Rozan, and I will talk about K-modality, as Liz said. This is a joint work with Dan Aron. A sequence sigma over a fully ordered set is said to be K-modal if there are at most K peaks and valleys in sigma, excluding the endpoints. In this example, we have 1, 2, 3 such peaks and valleys. The special case of K equals 0 is uniqueness, which is just either upward or downward monotonicity. And the special case of K equals 1 is unimodality, as can be seen in this example. Let sigma be a sequence of length n. Our task is to decide whether sigma is K-modal or is epsilon far from being K-modal. And we focus on three main things. First, we focus on sample-based testing. We are not allowed to use queries, only samples. Our second focus is the distribution-free model, where samples are chosen according to an arbitrary probability distribution. And our third focus is one-sided error testing. So we must accept if sigma is K-modal. The distance from K-modal is measured with respect to P. That is, the pair sigma P is epsilon far from being K-modal if the minimum weight of symbols that should be modified to make it K-modal is bigger than epsilon. We note that most previous property testing results are with queries and under the uniform distribution, and not in the distribution-free model with samples. Okay, since we are focused in the one-sided error testing model, our question is actually the following. What is the minimal number of samples such that for every pair sigma P that is epsilon far from K-modal, a sample of size S from sigma contains evidence that sigma is not K-modal with probability at least 2/3. The number of samples may depend on n, k, and epsilon, and the samples are chosen according to P, to the distribution P. Previous work. It is known that a square root of n over epsilon samples are both necessary and sufficient for testing monotonicity and uniqueness under the uniform distribution. And this raises some natural questions. First, how does the sample complexity increase as k increases? And second, what is the effect of having a general underlying distribution? I'll try to answer this question in the talk. Our first result is that the sample complexity of distribution-free one-sided error sample-based testing of K-modality is square root of Kn log K over epsilon. And our second result is an almost matching lower bound. We show that square root of kn over epsilon of samples are necessary for this task. Our third result is completely tight bounds for the case of uniform distribution. We show that in this case, square root of kn over epsilon samples are necessary and sufficient. And in this time, epsilon is inside the square root, not like the distribution-free case. In particular, our first result fixes a claim and argument of Goldreich and Ron for distribution-free sample-based testing of monotonicity, which is a special case of our property. The following folks study related properties of functions over one-dimensional domains. Some of them are also extensions of monotonicity. And you can see our paper for more details. I'll now share a few words about the very high-level idea of the proof of our first result. So our first ingredient in the proof is a structural claim. We show that we can divide any sequence sigma that is epsilon far from K model as many consecutive subsequences that are relatively far from being upward monotone and downward monotone alternatingly. And we know that the subsequences are not disjoint, they overlap, as you can see in this illustration. And the fact that they overlap is crucial to the correctness of the claim. Our second ingredient is a probabilistic one. We show that square root of 1 over delta beta samples are sufficient for detecting a violation to monotonicity in a sequence that is beta far from monotonicity, where delta is just the minimal weight of a symbol in the sequence. Combining the ingredients from the previous slide, we can obtain that if sigma is epsilon far from K model, then with high probability, a sample of size square root of Kn times log K over epsilon contains a K+2 pair sequence, which is a sequence of the following form. It has an ascent and then a descent and so on, just as in the illustration. And we observe that the existence of such a K+2 upward pair subsequence in sigma implies the existence of a violation to K modality in sigma. We prove this by just gluing together all these ascents and descents in order to get one big violation to K modality. This implies our first result, the upper bound for the distribution-free model. Here's a quick recap of our result, and thank you for listening to my talk.
Thank you, Asaf, for the nice talk. If anyone has questions now, we have quite a bit of time for questions, actually, so please feel free to unmute yourself and ask. Okay, maybe I can kick off with a question, actually. So what are some natural applications of K modality testing?
So it's mainly a very natural extension of monotonicity, which is very widely studied. I'm not sure about a specific application, but I hope and I think that this work may be helpful in order to generalize this research to some more generalized posets, like maybe hypercubes and so on, as many works in this type of testing monotonicity and its extensions rely on reductions to the case where we test the property on the line on 1 to up to n. So I hope that in this case it will be also true.
Cool, thanks. Any other questions? I think we have time for maybe one more if we want. Okay, I guess let's go ahead with Nader's talk. So the next talk will be by Nader Bshuti, and the title is Almost Optimal Testers for Concise Representations. So,
okay, can you hear me? Yeah, okay, good. Okay, so the model of testing in this paper is the distribution-free testing model, where the tester has access to a Boolean function with n variables through a black box that gives the value of the function in any point x, and an oracle that gives a labeled sample according to a distribution t that is unknown to the tester. Now, if the function is in the class C, then the tester should, with probability at least 2/3, accepts. And if the function is epsilon far from every function in C with respect to distribution T, then the probability at least 2/3 the tester reject. Now, we're interested in testing subclasses of K-junta. K-junta is a class of functions that depends on at most K variables. And we want to do it with query complexity that depends on K, but independent of the number of variables N. Okay. So this is the first paper that gives such tester, but under the uniform distribution. This paper improved the query complexity of the first paper. There are many other papers that also give some results, but all the papers give results for the uniform distribution model. We give testers that achieve optimal query complexity and a distribution-free testers with query complexity independent of N. So here are some results. So here D is the distribution free and U is the uniform distribution tester. So for example, for this class, we have almost optimal polynomial time tester and distribution free that has complexity that independent of N. I'll sketch now the tester. It's a very simple tester. So the function is either in the class C or epsilon far from the class C. So the algorithm first partition the coordinates into enough sets such that with high probability, if F in C, then each relevant variable of F, that is the variable that F depends on, falls into different set. We call a set that contains a relevant coordinate a relevant set. Then we binary search for enough relevant sets such that the projecting the variables in the other set to 0 gives a function that is close to F. This is the function H. So it is enough to test H. Now, of course, if we find more than K relevant sets, then we know that it is not K-juntas, and so in particular, it's not in the class C. Then we define a function G that is equal to H, where in all the coordinates of the relevant set Xi, we substitute the relevant coordinate in this set. Now, finding the value of the relevant coordinate is in each relevant set is done by a self-corrector. So it is possible to query the function G. Now, the function G depends on at most K variables. Now, if F is in C, then H is also in C. And if F is far from C, then H is far from C. And then either if G is far from C, so we either H is far from, either H is far from G or G is far from the class, okay? So we do two tests now. The first is testing if H is far from G. This can be done with order 1 over epsilon labeled example according to distribution D. And the second is testing if G is epsilon is far from C. The number of query in the second test is independent of N because G is a function on at most K variables. So this is the main idea of of course, there's many details of this algorithm, but this is the main idea of the algorithm. So this is the first tester I have, and it's a distribution-free tester. The query complexity is in each stage of the tester is independent of N. So, and this gives the distribution-free tester. The second tester we have in the paper is under the uniform distribution for classes that can be approximated by K junta. The tester we give makes optimal number of queries, or almost optimal, to log K, log factor. For example, for the class of D and F with S terms, the main idea is we run the first stage of the previous tester, but this time with a random uniform projector W, and not a zero projection like we did before in the first tester. The reason is that when we do that with high probability, the large terms in the DNF are zero, and the tester runs as if the target function is a DNF with terms of size order of log S, which is order of S log S junta. After finding a function f hat that contains the influential terms of f, we run the previous tester on f hat. So this is the main idea of the second tester. And this gives almost optimal testers for many classes. That's it. Thank you.
Thank you for the talk. If anyone has any questions, feel free to unmute your microphone and ask.
Maybe I have a question. Maybe we'll see if the answer won't be a little too long. But so can you say a few words about what is the source of your ideas that allowed you to get both the generalization to distribution free and also the improvement over previous work? Right? So what are, if you can kind of pinpoint the points where you have like the new ideas that really allowed you to get something stronger and better?
Yeah. So the new idea here is restricting the function to at most K sets, each contain at most one variable. So this is a new idea. I use this idea also in a previous paper for learning K junta under any distribution-free model. The other idea here, as far as I know, to the best of my knowledge, is new. Okay, using self corrector for finding the value of the relevant. Finding the value of the relevant variables in every block, and it uses the first stage. Also, I build here witnesses, and using witnesses, I am able to find the relevant variables in each block. So this is, I would say, similar to the idea of the first paper on distribution-free tester for K Khunta of Rocco and others. Okay, so it is similar but not exactly the same idea. Okay. They did something else. So I guess that's about it. I don't know if
Okay, thanks.
okay.
Okay, thank you, Nader. And let's have Carl Wimmer set up now. So the next talk will be by Carl Wimmer about testing data binnings.
All right, can everyone hear me? All right, oops. So I'm going to be talking about testing data binnings. This is joint work with Clement Canon from IBM Almaden. So this is a testing paper, a little bit different than the ones that we've seen so far in this session. We're talking about distribution testing here. So we say that an algorithm tests a property P of distributions if given access to samples from some unknown distribution little p. If P really does have the property capital P, then the algorithm accepts with probability at least 2/3. And if little p is far away from having property capital P, then the algorithm rejects. And we're talking about the standard distribution testing model here. So the notion of distance we're talking about is total variation distance. And we're thinking about these as being distributions here over the integers, say 1 through something like n. And our goal here is to minimize the sample complexity. How many samples do we need to see in order to be able to achieve this guarantee? So that handles the testing part of the title. So what is a data binning? So we'll talk about that first here. So formally, little p is a binning of some distribution Q when these distributions are over possibly different domains. And we'll think about capital N is much larger than K. And so if we can partition the interval, the integers 1 through capital N into K intervals, such that this distribution over K, the ith element of Q, has a probability mass that's the total of everything sort of in its bin or in its interval, then we say that P is a binning of Q. Again, thinking about these intervals as bins and hence the name binning. So to get a little sense of what's going on here, oops, let me talk about this first. A different way we can talk about this. And this is a different viewpoint that I think is helpful, is to think about, instead of an interval partition, to think about some non-decreasing function f, and then we can think about f pretty much defining the interval partition here. So let's look at an example. So if we look at these two distributions here, so is little p a binning of little q? And so the answer here, without taking too much time, is yes. And so to color things, that will make things a little bit easier to see, that the first element in Q that has a probability mass of 0.5, and the first 3 elements of little p also have a total probability mass of 0.5. The second element in Q has a probability mass 0.3. The sum of these next 4 guys has a probability mass of 0.3, and then similarly for the black things on the end here. Another sort of cute way to see this is if we look at a pie chart for these distributions, then we can see that these pie charts would look almost exactly the same, because again, these are the same distributions as before. So the pie charts look pretty much the same because P is a binning of Q, except that we see a couple of cracks between the elements in P. So going back to our non-decreasing version then in this example, it's not too hard to come up with what this function would be. And similarly for the interval partition version, here it's not too hard to see what would happen if we look at this same thing here, that the interval here is, the intervals are 1, 2, 3, 4, 5, 6, 7, and then the single 8 by itself. So like we would expect then at this point, if we have a known distribution Q, let's talk about our testing problem, and we have sample access to an unknown little p, so we get samples from P, we can ask for as many as we want, we're trying to use as few as possible, and we have this known Q that we're thinking about. So is P a binning of Q? And so this problem, to our knowledge, has not been studied in the literature before. So we give upper and lower bounds for this that are fairly close. We give an upper bound that we can do this with K over epsilon squared samples, and a lower bound that's roughly K over epsilon. Notice that in both cases here, capital N does not occur here at all. So this is completely independent of capital N. And so we'll take a moment here to talk about these at a high level. So for the upper bound, there's not too much that's going on here. We take this notion of AK distance, which has been studied before. This is a distance between 2 probability distributions over the same domain. That essentially says that no matter how we try to bin these things, if we use a common binning for each P and Q, and we look at how far away these binnings are from each other, then the AK distance kind of tells us, well, what's the worst that could happen over all possible binnings? And nice thing about AK distance is that this is something that we can actually work with here, given these probability mass of an interval is the sum of the probability masses of things inside that interval. So by VC dimension arguments, we can actually learn an unknown distribution to AK distance epsilon with about K over epsilon squared samples. This is something that's been used in a couple property testing papers. There's Dike Nicholas et al. And Chan et al. There listed. And because this is talking about partitioning into K bins essentially, then we have to be a little bit careful, but what's not too surprising is how we would run our algorithm then is to just learn the distribution to AK distance epsilon. And then once we have our known Q, we have our hypothesis distribution P prime that we know, then we can just check if it's close to a binning of Q or not. And step 2 here takes no samples at all because we have all of our information, but we can do this efficiently with a dynamic program in time that's polynomial in capital N. And so that's essentially the upper bound. There are a few small things that I'm kind of kicking under the rug here. The lower bound, we won't have time to go through the whole thing, of course, but I wanted to mention the highlights here. One thing that's maybe an interesting thing to an aside is we study this problem that we call identity up to binning, which means that we say that it's the same problem as data binning, except now we're going to assume that the support sizes of both P and Q are K. This unknown distribution is still, could be, have things from the interval 1 through capital N, but there's only K elements that have non-zero probability. And so this is kind of like an identity testing type problem, which has been studied a lot in the foundational problems in distribution testing. So that changes our definition a little bit here, that F here we can think about as an increasing function. And then all of the bins really only have one element in them. Or if we think about the interval partitions, each interval is only allowed to have one element with non-zero probability. So in the reject case, though, we're still going to make sure that we reject anything that's far from any binning. So maybe it's possible to get close to this distribution, maybe not by using something that looks like this here, but with something that maybe we put a bunch of elements in one bin and leave one bin empty and somehow get close in variation distance. So in the reject case, we want to make sure that that cannot happen. And just give us some sort of bearing on what we're talking about here. Identity can be done with root K over epsilon squared query complexity. And so this problem should be a little bit only harder than that. So what do we actually do here? Our notion here is that, well, if we think about capital N being very large compared to K, then the actual names in the support of P aren't very helpful. I mean, if we see a sample that looks like this, and K, if you think about it small, in the teens or like 100 or something, and you see these 7-digit numbers, it's not really clear where they are in the distribution. I mean, there could be nothing between, the 5 millionth and 8 millionth thing here. There could be lots of elements between there. We don't really know. So the idea here that we say is that we take what we call a fingerprint of samples to be just the frequency vector of what we see. And it's going to be in order, so it's not just the unordered thing, it's going to be in order. So here we saw smallest element once, we saw the middle element twice, and we saw the largest element once. This seems like the most helpful information that we have. And our theorem is that as long as capital N is large enough, then this is really the best that we can do, is just look at these objects here. And so then we might as well think about P as a distribution over K, and then it very much is like an identity testing problem, except that we have restricted information from our sample. Now, the proof here goes through a Ramsey theory argument, so the capital N here for large enough really does have to be, the large here is emphasized. And then from this point, we give two distributions that if you don't have very many samples and you're only allowed to look at fingerprints, then the identity up to binnings problem can't be solved, which means that the data binnings problem needs as many samples as well. So this is back to our conclusions slide here. Open questions, we could ask for tighter dependence on these things. K here are pretty close. We have good dependence on K here. Epsilon, we have epsilon squared versus epsilon, so there's some room there. And also the capital N that we require is very large because we're going through a Ramsey theory argument. We could also ask for the case where both P and Q are unknown. So we'd have to sample Q as well to try to see if P is a bitting of Q rather. And we could also ask this question over other domains like, grids or hypercubes or something like that. All right, thank you for your attention.
Thanks, Carl, for the nice talk. If anyone wants to ask a question, please feel free to unmute yourself and ask. I have a question actually. So what about making structural assumptions on P and or Q, for example, that the, you have a lower bound on the probability for any element?
Yeah, so that's a good question. So our distributions that we come up with are actually kind of uniform. So the lower bound here, that hard distribution for our identity up to binnings problem, uses things where there's actually only two different probability masses. So the histogram of the distribution would be sort of nice looking, where half of the elements are slightly below the average probability and the other half are slightly above.
Okay.
So for that specifically, then it turns out that that's going to give us pretty much the same lower bound, at least what we have here. But we didn't think too much about what happens if we have structural things, if we assume, X property of the distribution.
Nice, thanks. Okay, so I guess we are starting our final talk of the session. Anoop Bhattacharya will be telling us about disjointness through the lens of VC dimension, sparsity, and beyond. Okay, great. So take it away, Anoop.
Hello, can you hear me?
Yes.
Okay. Hi, I'm Anoop and I will talk about disjointness through the lens of VC dimension. And this is joint work with Saurabh Chakrabarty, Arijit Ghosh, Gopinath Mishra, and Marasi Parasar from Indian Statistical Institute in Kolkata. We use the standard communication complexity setup where Alice and Bob has inputs A and B to compute the function FAB. And we define the communication complexity of the function as the number of bits that needs to be exchanged between Alice and Bob to compute function f. There are many variants that are studied around here, and the deterministic communication complexity we denote by DF, the randomized communication complexity we denote by RF, the one-way deterministic and randomized communication complexity is denoted as D arrow F and R arrow F. And we use a public coin communication model here where we assume that Alice and Bob can share the random bits. Okay, and it is a widely studied, all of these are a widely studied model of computations with numerous applications in complexity theory. And one of the most well-studied problems in this area is the set disjointness problem. So we start by defining the set disjointness problem. Let U be a universe of the first of the set with first n natural numbers. Whenever we use the universe U, we denote the first n natural numbers. Alice receives a set A and Bob receives the set B as a subset of this set, and they want to determine if the sets are disjoint or not. So this is as known as the disjointness problem. This is a very well-studied problem, and it is known that the deterministic and randomized communication complexities for this problem is omega n. We next define the set disjointness problem on the restricted set systems. So what do we mean by that? Now we define S as a collection of subsets of this universe, and we require A and B to belong to this collection. So we also assume that both the pairs know this collection S, okay? And under this restriction, we define with this as the deterministic combination complexity of disjointness under this restriction S, similarly for the randomized and one-way randomized communication complexities. So one such example is as known as the sparse set disjointness, where it is known that all the sets have size at most set T. where we denote this by ST, and here A and B are belong to this collection ST. It is also known that the randomized communication complexity of sparse set disjointness is theta t. Okay? So the main motivation of our work is to study the communication complexity of set disjointness parameterized by some complexity measure of the underlying set system. For example, as mentioned before, sparseness was one such measure of the complexity of a set system. And the communication complexity of set disjointness was studied under this measure of complexity. VC dimension is another well-studied complexity measure for set systems. And just note that sparse set systems have bounded VC dimensions. So the main objective of this work is to study communication complexity of set disjointness on set systems with bounded VC dimension. More precisely, here is the main question that we ask in this paper. Let US be a set system with VC dimension at most D. Then what can we say about the deterministic randomized and one-way randomized communication complexities as parameterized by D? So we do a brief VC dimension recap where let US be a set system with U being the universe and S be the collection of subsets. And the VC dimension is defined as the size of the largest size subset that is shattered by the set system. For example, VC dimension of the T sparse set system, where all the subsets have size at most T, is at most T. Okay. So now let us see what are the implications for set systems with bounded VC dimension. Let NS be a set system with VC dimension at most D. Then Sawyer-Seller lemma tells that the number of subsets in the collection is at most N by D whole to the D. So using Sawyer-Seller lemma, it is not too hard to prove a one-way deterministic communication complexity of order of D log N over D for the disjointness problem. So bounded VC dimension implies disjointness as order of D log N over D communication protocol. Okay. The main work in this paper goes into proving almost matching lower bounds for one-way randomized communication complexity and one-way randomized complexity of this disjointness problem when the collection has bounded VC dimension. We also study a related problem known as the set intersection problem, where Alice and Bob are, as before, Alice and Bob are given two subsets and they want to compute the exact intersection. Again, from the Sawyer-Seller lemma, it is easy to prove an upper bound of order of D log N over D. And the main work goes into proving matching lower bounds for randomized and one-way randomized communication complexity of this intersection problem. In brief, here are the main results of this paper. So the first row is the, we just mentioned just to compare with the results. This is for the T sparse set system. And for disjointness, the first column shows this disjointness, randomized combination complexity disjointness and one-way combination complexities. The second row is our results marked in blue for set systems with bounded VC dimension bounded by D. The first result is, the first column shows this result, the randomized communication complexity. This result is tight up to a factor of log N over D. And for the rest of the cases, we have tight bounds. Since I will not have to talk about the lower bounds in detail, I'll just mention that we use geometric set systems to prove these lower bounds and use number theoretic arguments. For more details, please see the full version of the talk and the paper. Thank you.
If anyone has any questions, please go ahead and unmute yourself to ask.
I mean, do you think the log is tight in the lower bound, or is that?
So we tried to match that lower bound, of course, but we could not. We think there may be some barrier, but we are not very sure. We did not try too hard on this.
But you think this is the correct answer? The upper bound should be divided by log.
No, I think we think it should be D log N over D, but we don't know how to prove.
So I had one question, Anup. This upper bound using the Sawyer lemma, does it apply to a more general thing than just disjointness?
What do you mean by more general?
I mean, could you state a communication upper bound for some more general problem? How specific is that result to disjointness?
No, as in here, for the set intersection problem also, we use the same Sauer-Seller lemma to prove the upper bound. So yeah, it may be possible to apply this to like other problems with bounded VC dimension.
So would it be possible that if the VC dimension is a small, Bob can just send his entire input in this much communication to Alice? Sorry, Alice or Bob, either of them. If the VC dimension is that small, couldn't one of them send the entire input to the other player?
VC dimension may be small, but the size of the set may be large, right?
I mean, but they know the set S, and they just need to know the index of.
Right.
So there are n over d to the power d different sets.
Right, exactly. That's how we proved our upper bounds. Right?
Okay, good. Yes, good. So the upper bound isn't in fact about the disjointness problem, right?
Hello, is that a question?
Just reconfirming something that I had suspected, but Sefer clarified it for me. Yes,
okay.
Thank you. Yeah.
Okay, excellent. So if there are there any more questions? I guess we have time for maybe one more question if we want.
Yeah, so I wanted to ask, can you just in like a couple of words about your lower bound? Is it some information complexity lower bound or discrepancy or anything, or?
Okay, so we use like geometric set systems. It's like, say, you have a two-dimensional grid on which there are like endpoints, and Alice has a line and Bob has another line. So the question is whether these two lines intersect on one of these grid points. And so we use this number theoretic, like the slope, what are the slope of these two lines, the intersection criteria, and using that we prove this lower bound.
So, but just one quick, I guess, follow-up. Does it reduce the lower bound at some point to the original set disjointness lower bound, or you are giving a, like basically a new proof of set disjointness?
So here, say this reduces to the factoring problem. I mean, so factoring means given two integers, whether one is factor of the other.
Okay. I see. Okay, thanks.
Thank you.
Okay, so if there are no more questions, thank you once again to Anoop, and thanks also to all of the speakers in today's sessions and to the audience who was lovely and asked many interesting questions and were very engaged. So thanks so much, everyone. See you tomorrow at random.